Welcome to the first video for week 11 and lecture 10. This week we're going to talk about comparators, half and full adders, multiplexers and demultiplexers. So the previous week, week 10, the current week, week 11, and the following one, week 12, are very closely related because they lead to common conclusions. So in the previous week, you've seen how to use exclusive OR, which is an important gate in some common applications including encryption, parity bit generation and checking. We've also talked about adders and subtractors. This week we're going to talk a little bit more about comparators, and we're going to introduce and discuss multiplexers and demultiplexers. On the next week we're going to see a few more things, decoders and encoders, as well as the arithmetic logic unit. So let's start. So as you've seen, XOR and XNOR, which we also clarified that it can be used as an equivalence gate, they can be considered as one-bit comparators. And what does that exactly mean? Well, let's take XOR as our example. It will output 1 only if and only if the two inputs are different. Now let's take a look at the equivalence. The equivalence is the negation of XOR. So it outputs 1 if and only if both inputs are either false or both of them are true. Therefore, we can say that in the case of XOR here, the active high output diff is asserted if the inputs are different. Likewise, regarding the equivalence gate here, we can say that the active low output EQ is asserted if the inputs are different. Now let's generalize to the case of an n-bit comparator. What you see here is the comparison of two 4-bit words. What you can do is pass each pair of bits through a XOR gate. Find the differences and then pass them through an OR gate. Now, how does that work? If the two 4-bit words are the same, this means that all the XOR gates will output 0. On the very contrary, if at least one of the pairs is different, then one of the diffs is going to be equal to true, equal to 1. So passing the results here works as the final verdict. If at least one of the pair of bits is true, then the last OR over here is going to output 1. So this is going to signify that there was a difference in at least one of the pair of bits. Notice that this is a case of parallel comparison, because you compare the bits in pairs in parallel. Also, notice that since the OR gate is associative, this always works as a tree-like structure. Typically, we use NOR NAND topologies because they tend to work faster. Notice the NOR gates here, and notice the NAND gate here. Now, this can result, as you can easily notice, in a significant number of logic gates if n is a big number. By n, we refer to the number of input, the input variables here. So just consider how many 4-bit gates are needed to compare two 64-bit words. This is for 16 bits. Then you repeat it for all of the 64 bits. You got the NOR gates here, then you got the XAND gates here. And then finally you need an OR gate here. So is it necessary really to compare all the pairs of bits? if you only care to find if at least one of the pairs is different, then this is what you want to look at. So how would you do that? Suppose that you're checking the equivalence of the nth bit from two words, x and n. The only thing you need to do is check what the equivalence gate of the previous pair said. You can do that by having an AND gate at the end over here. The result of this AND gate here verifies the equivalence or not of all the previous pairs of bits. So all the previous pairs of bits from pair 0 to pair n-1 can be seen from the output of this AND gate over here. And this is how it looks in the general case. The output over here, ec0 reports 0 if any of the previous pairs of bits are different. So let's try to chain them together and at the same time use an example and see how it works. This is how it would look from the inside. This is how it would look from the outside as an iterative circuit. Notice what happens here. If you pass 0 and 0 here and 1 from the previous level, the results passed to the first AND gate are 1 and 1. This verifies that there was no difference in the bits that were examined both at this level and in all previous levels. So the output is passed here to the next level as 1 in this iterative circuit. Now check what happens here. The inputs at this circuit, at this iterative circuit, on this part here, are different. Well, the result's going to be 0 here, and even though the previous levels were not different, the output will be 0. Regardless of what the inputs are here, in this case they are the same, the output from now on, it will always be 0. And this is how this iterative circuit works as an n-bit comparator. Now, having the previous example in mind, let's see how a general structure of an iterative circuit would work. So at the first level, you have some boundary inputs coming externally. And from now on, with each layer, you will be having a cascading output used as a cascading input for the next layer. So C1, for instance, is a cascading input when we talk about this circuit. And there you will have a cascading output, which will be passed next to the next circuit, and so on. And at the end, you will have some boundary outputs, which, depending on the use of this iterative circuit, they can be ignored or not. Remember that in the previous lecture, we talked about 2's complement addition. One of the boundary outputs could have been, for instance, the possible overflow, which could be neglected or not. Besides this, you need primary inputs, which will yield primary outputs. In the previous example, primary inputs were the pairs of bits that we were comparing. And the primary output in each and every circuit would have been whether or not the bits were equal or if they were different. So after this small introduction, we will proceed with our next video, which is going to focus on multiplexers and demultiplexers, decoders and encoders. The intended learning objectives after weeks 10 and 11 are that you should know what adders and subtractors are and how they work, and likewise about comparators, multiplexers and demultiplexers, decoders and encoders.